In this video, we're going to continue solving optimization problems. This is problem number 3. A box is constructed so that the base length is 3 times longer than the base width. The material used to make the top and the bottom costs $10 per square foot, and the sides cost $6 per square foot. If the box must have a volume of 60 cubic feet, determine the dimensions that will minimize the cost to build the box. A box is a rectangular solid, so let's draw a rectangular solid. With dimensions of, let's call the height as h, the length as L, and the width as W. Okay. And then we have constraints here. The base length is 3 times longer than the base width. So we can express the length, or L, as 3W. And then we have costs per square foot. In other words, these are costs per area. Okay. For the top and bottom, let's call it C sub TB, and that's $10 per square foot. If we multiply this value, $10 per square foot, to the area of the top and bottom, then we'll get the total cost for building the top and the bottom of the box. Same with the sides. The sides cost $6 per square foot. Multiply this value to the area of the sides of the box, then we get the total cost for building the sides of the box. Okay, so we're dealing with costs, and the problem wants to minimize the cost. So let's define the total cost for building the box as C sub T, and then we also have the volume. It's fixed at 60 cubic feet. Then we are asked to determine the dimensions. That's the length, the width, and the height. That will minimize the cost. So required is L, W, and H at minimum C sub T. Okay, so we want the minimum possible cost. Therefore, the primary equation is the equation for the total cost. Right? So let's set up the formula for the total cost. Remember, I mentioned earlier that if we multiply the costs per square foot by the area, we'll get the total cost. So to find the total cost, we have to multiply the costs for building the top and the bottom and the area of the top and the bottom, add this to the cost of the sides times the area of the sides. So this is now our working equation for the total cost. So let's plug in the values and the equivalent expressions. Cost of the top and the bottom is $10 per square foot, so we can just put 10. Area of the top and bottom in this case, so we have the top here and the bottom. The area for each is length times width, so we have 2 times length times width, okay, plus cost for building the sides, $6 per square foot, so we can just put 6. And then area of the sides, so we have 2 sides, okay, so this one, first set of sides, the dimensions are W and H. Okay, so for each face, that's W times H. Then we have 2 of them, so the area is 2 times W times H. Okay. And then lastly, we have these faces, the front and the back, and then the back. You can just imagine the back portion. So the dimensions involved are the length L and the height H. So for one face, L times H, then we have two of them. So plus 2 times L times H. Simplify this further. You have 20 L times W plus 12 W times H plus 12 L times H. And as you can see, this equation is in terms of L, W, and H, three independent variables. So we have to express this equation in terms of a single independent variable using the constraints. Remember that the length is 3 times W, and then the volume of this box is 60 cubic feet. Volume for rectangular solids is L, W, and H. Plug in the value for the volume, 60 cubic feet. Then we have L, W, and H. Again, we know that L is 3W. Then we have W times H. This is equal to 60. We can isolate H. Isolating H, we get what? 20W squared, right? Plug in these equivalent expressions for H and L to the primary equation, which is the equation for the total cost, so that it will be reduced in terms of a single independent variable, in this case W. Okay, all right, so we have the total cost equal to 20 times L, where L is 3W times W, plus 12 times W times H, where H is 20 W over W squared, plus 12 times L, again L is 3W, and then H is 20 over W squared, right? So let's simplify. C sub t is equal to 20 times 3, that's 60. W times W, we have W squared, plus 12 times 20, that's 240, right? Then we have W over W squared, that's over W, plus 12 times 3 times 20, that's 720. W over W squared, that's over W. Okay, we have like terms here. You can combine them so that our total cost now is 60 W squared plus 240 plus 720, that's 960 over W. Taking the derivative of the total cost with respect to W, or the width, we'll get 120 W minus 960 over W squared. Okay, set this to 0, then we can combine the two terms as a single fraction. So let's take the LCD, W squared. uh, this will become 120 W cubed, right? Minus 960. And then we'll solve for W. Okay? So if you multiply both sides by W squared, we'll get 120 W cubed minus 960. If we transpose 960 to the other side, so 960 equal to 120 W cubed. We can divide both sides by 120 so that we get 960 over 120, that's 8, right? Equal to W cubed. Take the cube root of both sides. Let's rearrange this first. So cube root of both sides. So we'll get W equal to 2. And the unit is feet. So this is now the width of the box. Solving for the length, we know the length as 3W. So the length is 3 times 2. Therefore, the length is 6 feet. And then lastly, solving for the height, we obtained the equivalent expression for the height earlier as 20 over W squared. So let's plug in W equals 2. So we get 20 divided by 4. Therefore, H is equal to 5 feet. So these are now the dimensions of the box that will minimize the cost having a fixed volume of 60 cubic feet. Okay, so if you want to check, let's try to solve for the volume for the box. Again, the box is a rectangular solid, so length times width times height. Let's plug in the values. 6 for the length, width is 2 feet, the height is 5 feet. This should equate to 60 cubic feet, right? 6 times 2 is 12, 12 times 5 is 60. Next problem, two poles, one is 6 meters tall and the other one is 15 meters tall, are 20 meters apart. A length of wire is attached to the top of each pole and it is also staked to the ground somewhere between the poles. Where should the wire be staked so that minimum amount of wire is used? Let's sketch. Let's say this is the ground and this is the 6 meter tall pole. Then this is the 15 meter tall pole. They are 20 meters apart. A length of wire is attached to the top of each pole. They are connected by a wire at the top, and this wire is staked to the ground. This means that somewhere between the two poles, the wire is staked to the ground or driven to the ground so as to support the two poles. So this is staked to the ground. Okay. so that it will look like this one. Okay, so this is roughly the illustration for the problem. We are asked to find the point, so this point here, where the wire is staked. So this is somewhere between the two poles. We don't know that yet, so let's call this part X, for example. If this is X and they are 20 meters apart, then this portion here is 20 minus X, right? What we want is the minimum amount of wire. This means that we have to minimize the length of the wire. Okay, let's say the length of this portion is L sub 1 and the length of this portion is L sub 2. Let's call the total length of the wire as L sub t, and it's equal to L sub 1 plus L sub 2. Okay. Again, we are asked to find where should the wire be staked. So that's x meters from the 6 meter tall pole, or 20 minus x meters from the 15 meter tall pole, minimizing the length of the wire. Let's solve. Our primary equation is the equation for the length of the wire, the total length, L sub t. This is equal to L sub 1 plus L sub 2. If you look at the sketch, as you can see, we have right triangles. Therefore, we can apply the Pythagorean theorem, right? Let's look at L sub 1 first. This is the longest side on this right triangle, okay? And using the Pythagorean theorem, the measure of L sub 1, the longest side, or the hypotenuse, is equal to square root of the sum of the squares of the other two sides, right? So 6 squared, that's 36, plus x squared, that's L1. Let's move on to L sub 2. L sub 2 is also the longest side on this right triangle here. So its measure, or its length, is equal to square root of 15 squared. So 15 squared is 225, plus the square of this side. So 20 minus x squared. Okay, some of you might expand this expression here. I suggest that you leave it as is for now, because it will be more convenient later on as we continue with the process. Okay, so this is now our primary equation, the equation for the length of the wire. Okay, let's take the derivative with respect to x. This is equivalent to 36 plus x squared raised to 1/2. So using the power rule, we have 1/2 36 plus x squared raised to -1/2 times the derivative of the inner expression. So 0 plus 2x, plus the same process. So we have 1/2 times 225 plus 20 minus x squared raised to 1/2 minus 1/2, or 1/2 minus 1, that's -1/2. 1/2, and then derivative of the inner expression, so 2250, and then derivative of this one, so 2 times 20 minus x. 2 minus 1 is 1, so raised to 1. And then again, derivative of the innermost expression. So 20 minus x, derivative is -1, right? Set this to 0 and then simplify. Okay, so we can cancel out 2, right? Then we have convert this to a positive exponent, so it will be transferred in the denominator. You have x, and then we can express this as a radical, right? So square root of 36 plus x squared. Then for the second term, we have a factor of -1, so this becomes minus, then cancel out 2. So we have 20 minus x divided by this expression. So square root of 225 plus 20 minus x squared. Solving for x, we can transpose this term to the other side of the equation so that it becomes positive. Okay, so we have 20 minus x all over square root of 225 plus 20 minus x squared equals x over 36 plus x squared. Okay, and then we cross multiply, right? So that you get what? 20 minus x times square root of 36 plus x squared equals x times square root of 225 plus 20 minus x squared. Okay, and then we can simplify this one by eliminating the radicals. To eliminate the radicals, we can square both sides of the equation. Okay, so if we square both sides, this becomes 20 minus x squared. This will be reduced to 36 plus x squared, right? Equals, this one becomes x squared, and then the radical will be eliminated, so 225 plus 20 minus x squared. Let's leave the left side of the equation as is for now. 20 minus x squared, 36 plus x squared equal to, and then let's distribute x squared. So we get 225x squared plus 20 minus x squared times x squared, right? If you look at this equation, we have common factors, 20 minus x squared, and this one, we have 20 minus x squared on the other side. So we can combine the two terms, right? So if we transpose this term, for example, to the left side, we'll get what? 20 minus x squared, or 20 minus x squared, 36 plus x squared minus this term, so 20 minus x squared times x squared equal to 225x squared. Okay, then we factor out the common factor, which is 20 minus x squared, so that for the first term we are left with 36 plus x squared, minus for the second term we are left with x squared, so minus x squared equal to 5x squared. Cancel out x squared so that we'll be left with 36 times 20 minus x squared. So 36, 20 minus x squared equal to 225 times x squared. Okay. Let's take the square root of both sides. Okay. Square root of 36 is 6. Square root of 20 minus x squared. So this becomes 20 minus x equals square root of 225, that's 15. Then square root of x squared, that's x. We can divide both sides by 3. So that's 6 divided by 3. This becomes 2. 20 minus x equals 15 divided by 3. That's 5. So 2 times 20, 40 minus 2x equals 5x. Okay, so we have 40 equals 5x plus 2x. So that's 7x. Therefore, x is 40 over 7. The unit is meters. Okay. Therefore, the wire should be staked 40 over 7 meters from the 6-meter tall pole, or 20 minus x. So that's 20 minus 40 over 7. 20 minus 40 over 7, we have 7. 140 minus 40. So this is 100 over 7 meters. This is from the 15-meter tall pole. Okay, so it's either this one or this one. Next problem. A container in the shape of a right circular cylinder with no top has a surface area of 3 pi square feet. What height and base radius will minimize the volume of the cylinder? Okay, so we have a cylinder. Let's draw a cylinder. With no top, so it's open at the top. Okay, let's call the height h and the base radius, so let's call the radius r. Okay, the surface area is fixed at 3 pi square feet. And then we are asked to find the dimensions h and r that will minimize the volume of the cylinder. So our primary equation should be the formula for the volume of a cylinder, and that's pi r squared times height. Okay, so again we are asked to find r and h that will minimize the volume. Let's solve. Primary equation is the equation for the volume of the cylinder, so that's v equals pi r squared height. Okay, This is in terms of two independent variables, the radius and the height. So let's reduce this equation first in terms of a single independent variable using the constraint that the surface area should be 3 pi square feet. So formula for the surface area of a cylinder is 2 pi RH. This is the lateral surface area, okay, plus 2 pi R squared. This is if the top and bottom is present. However, in this problem, it is stated that there is no top. So our working equation for the surface area is this one, okay, where SA is equal to 3 pi. So let's plug in 3 pi equals 2 pi RH plus pi R squared. Pi is a common factor, so we can cancel out pi, right? And then we can solve for either the radius or the height. For this particular equation, it would be more convenient if we isolate h, or if we solve for h, okay? So h is equal to what? Three minus r squared. So we have 3 here, 3, then transpose this term, r squared. So 3 minus r squared. Then divided by 2r, right? Divide both sides by 2r, so divided by 2r. Let's plug in this expression to the volume formula. So V now is equal to pi r squared times height, where height is 3 minus r squared over 2r. Okay, we can rewrite this as pi over 2, then r squared divided by r, so r, and then distribute r. So this becomes 3r minus r cubed, right? Take the derivative with respect to r. We have a constant multiple rule here, and then 3r, derivative is 3, and then power rule for this one, 3r squared. Set this to 0 and then solve for r. Okay, divide both sides by pi over 2, so we can get rid of this factor. We'll be left with 3 minus 3r squared. Okay, so we can transpose negative 3r squared. 3r squared equals 3. Divide both sides by 3, so r squared equals 1. Take the square root of both sides, so r is equal to plus minus 1. Okay, it does not make sense that the radius is negative 1, so we can just take the positive value. Therefore, r is equal to 1. The unit is foot. Solving for h, so we have a formula for the height that we obtained earlier. Height is equal to 3 minus r squared over 2r, and then let's plug in the value for r. 3 minus 1 squared times or over 2 times 1. So h is equal to 3 minus 1, that's 2 divided by 2. So h is also 1 foot.